let's jump into something, again, extremely important. I have to do it the right place. Namely, what we call regression analysis, or maybe correlation analysis. Have you noticed any difference with me since last time? I didn't grow significantly older, I find, 1 week. That's not so bad when you're my age. I grew, finally. My parents told me all my childhood, don't worry, you'll grow, finally. Now it happened. At my 48th year, I grew. Oh, I complained about this one, right? Don't put this up, so at the end, I mean, you can't see me, I'll be down here. I'm the teacher. So I said, they need to at least see me. So I guess this is the TV solution or of being seen, right? Like that. I shouldn't have told you, of course. I should just have, like this. Okay. Anyway, here I am, grown 10 centimeters. The plan for today is this. I'm going to make a small sample with you, and then please join in a lot larger sample in my meeting room, and we'll have a look at the larger sample at the end. It'll take too long time for me to go on. Let's start and dwell on the plan at the end. I think that's better now. My plan was to do a little sampling of you related to height and weight. So that is a bivariate sampling, you could say. Let's go ahead and do it. Let me do it in R. And let's say I'm not going to ask any of the female visitors. You can share, if you want, you can share it with us on the internet, but I am still as old-fashioned, so I wouldn't do that. But I'll ask some of the young men in here if they want to play the game. If you don't want, just say I don't want to play the game. Should we start over here? I make a random sample. I flip the 100-sided coin here, whoop, and it hits you. Would you like to play the game? Would you give us your height?
My height is 195.
Yes, and your weight? Yeah, I could see that. Should we make a sample and let us take you?
180.
Yes?
And 85.
Good.
Could you make that?
Sorry. Just a sec. I forgot a little thing here. Okay, we continue. We flip the coin and we take you.
182. 110.
Good. We need some variability here. Let's flip the coin and take you if you want to play the game. Are you all giants or what? Sorry. Okay, let's flip the coin and any small guys in here? Sorry about yeah, let's you.
172. 66.
Oh, fantastic. Should we flip the coin? Do you want to play the game also?
183.
Yes.
65.
65. We play the game, and are you in the back? Behind, you want to play?
198 and 90.
Good. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. I'd like 3 more. Should we take you 2 guys up there? Would you want to be part of this?
173 and 69. 180 and 70.
Oh, these are good observations. Yeah. And should we flip the coin and take you before? Do we want to be part of you? Yeah.
192. 78.
78.
191 and 85.
I think that's fine. I think actually now I go to 11, and that's perfectly fine. Let's just check length of our height. Weight, sorry. 11. That's fine. We take 11. Let's do something. We just have to do a bit of height, weight. Height, weight.
Spell weight the wrong way.
Thanks. Where did I help me here? Ah, that's a classical one. Yeah, I do that often. Weight. Yeah. Here's the picture of the 11. What can we learn from this picture? That is the whole topic of today's lecture. That is looking at 2 different variables simultaneously and trying to be intelligent about that and learn from that. There are different ways of looking at such numbers, and there are different ways of doing the statistical thinking. And we're going to split it a little bit. In the first part here, I will mostly be talking about looking at the numbers and computing the things. And then the second lecture will be focusing on the new statistical thinking about this that you might not have met before. The first part, you may have met some of these things, I believe, in different places. What can we learn? Looking at these numbers. Anyone who want to speculate? Please?
Try to draw a straight line somewhere in the middle of all these points. Like that, yes?
Yeah.
You'll see that there's a relation between the height and weight.
Yeah, that's a very good, as it said, if you try to make a line, now I had the computer make a line for me. We'll get back to how we compute such a line, of course. That's a part of what we're going to learn. And we see a general tendency here that it seems like weight, generally speaking, across individuals are increasing with height. So the higher you are, the taller you are, the higher weight you have. Not surprising, of course, but we also see that it's definitely not a one-to-one relationship, right? There is a high degree of variability in this system. There is a high degree of, if we look at people that are, let me do like this. And let me go here. Wrong place. Let me go here. Let me do like this. Here we are. Then I have the relationship. I would, what I was going to say, for instance, if we look at people around 180 centimeters, of course we see what we already know. that some 180 centimeter guys are on the slim side and some 180 centimeters guys are not so much on the slim side, or on the strong side or not so strong side. Or we are biologically different, right? And we have also developed differently. So when you look at the population of 108 centimeters, we are not the same, you're not the same. I'm not part of this population. But anyway, you're not the same, but if we took people of my kind over here, the story would be the same. As I said, I was born almost 50 years ago with smoking and heavy metals and whatever was going on at that time. So you guys are being taller. Yeah. Another thing we could actually focus on, still part of my first thing here, is the correlation. What is that? We'll get back to the line in not so many minutes. There is another way, not the line, but there is a more symmetric way. You could say the line is a way to say how does y develop with x as a function of x. There is a kind of a symmetric way of telling the story about the relation between two things. And this is called the correlation coefficient. It describes, as I say here, how much linear relationship there is between two variables. And here is how we should compute it. Here's the definition in a defining formula. Please note when you look at this definition that basically only the standard deviations of x and y and the means of x and y is part of this computation. So in a way, we are not using any, technically speaking, we don't use anything more. However, there is a new combination of things here in this formula. In this formula, we combine x deviations with y deviations by multiplying x deviations with y deviations. And by combining x and y information like this in such a formula, we get a measure of how x and y are related to each other, are correlated. That's sort of a short description of what's going on. Should we just try, before I give some more details, actually, this formula is put in to R. There is a function that gives this value, and it's called core. What is the correlation? The correlation is 0.35 in this case. Let's write that. Please note that it's positive, it's above 0, it's smaller than 1. Such correlation coefficients are always between -1 and 1. 0 means, what does the different values mean? Let's have a look. I brought a copy from the book today showing that this was the little thing that I was going to look at. I think it's fair enough, I don't have to increase it. Here are the sort of the visual pattern of 6 different values of this correlation between two things. Let's see, the one that is closest to our height-weight example is the 0.5 case here. A clear, I would say, looking at 20 points like that, a clear positive tendency, right? There is a relation. It's definitely not a one-to-one, but there is a relation. That's a typical 0.5, and in our case, it's a 0.35 something. Yeah. Now, it could have been, depending, in other contexts, maybe I could have turned it around. Maybe the dependence will go down. Some things are related negatively to other things, so the tendency could be downwards instead, and then it would be a minus. It's a measure between 0 between -1 and 1. If we have patterns like this, we get closer to 1. And in the extreme case, if a correlation of 1, they're exactly on the line, right? Or they could be minus 0.9 here. Then what about the 0? Here is one example of a 0 situation. A lot of variability going on and no relation whatsoever between x and y, right? If you would try to put in a relation, it would be completely flat. No linear relation. That's the word that's also important to remember, because these data, if you would enforce a linear way of looking at things, if you enforced a linear way of looking at things, there would be a flat line telling the flat line here would be the best possible story of how y is related to x, because the way y is related to x in this case is highly nonlinear. So the correlation coefficient only tells the story about linear relationships. So a good thing to learn here is that when we look at correlations and correlations coefficients, we should always look at the data in one way or the other to go check whether we have, so if it's close to 0, it could be this situation or it could be this situation. And it's not good to go around and submit to your boss or to a scientific journal that x and y here have nothing to do with each other. And then when you plot them, you have a plot like this and say, whoa, yes, they're very closely related, but just in a nonlinear way, right? So that's a small thing to remember here. Let me just very briefly now think about this defining formula here. This combination of x deviations with y deviations. Why does that give? Why does that give a meaningful summary of the relation between x and y? Let us assume that we in the center, we have made a coordinate system of our data, which is in the center of x and center of y, right? So we take points in the center as the outset, which means that up here we would have a point where x is larger. Such a point here has that xi minus x bar is positive, right? X is larger than its x, the average of the x's. The y's are also larger than their x's in the first quadrant, right? The first quadrant are positive x's, positive y's. And when I take the outset as the origo, as the average of x and y, the first quadrant are all those points that has positive deviations, both in x and y. And positive deviations means that the product, I continue to mix those two, the product of these two, the product which enters the definition formula for the correlation coefficient, the product becomes positive, right? I did it again. I could see you were smiling in your November beard there. So sorry if I did. Don't know if it's a November beard. How could I know? What about these numbers down here? Well, in this case, they are both negative, right? Now I concentrate. When I multiply two negatives, they're also positive. Now I have shown you that the terms entering the definition formula of the correlation coefficients, if those terms primarily enter the first and third quadrant, which they will if I have a positive relationship, right? Then the correlation coefficient will tend to be positive. Of course, there could be a single one out there, but most of them, and the majority of them, those with the largest values, will contribute positively to the correlation computation, right? So having points like this, which I have, which we have in our height-weight example, points like this, they will produce a positive correlation. I was trying just to illustrate how the formula works on the data. That was just the idea of this, right? And vice versa in the other two quadrants, like this, right? That was the basic idea of correlation. Now we go to regression.